Okay, all right. Thanks for coming to the opening of the UNSOUND workshop. So I'm Lionel Parreaux, one of the three co-organizers of the workshop. Unfortunately, the others two cannot come today, so they will participate remotely. Okay, so this workshop is about the sources of unsoundness in type systems and verification. This is the second edition of the workshop, which had the first edition in Splash 2022. We're maybe thinking of having it every 2 years. So here's the program. We have actually two talks in the morning, in addition to this one. And then a few more in the afternoon with 3 remote talks, actually. One of the presenters was supposed to come, but he was stranded in the airport, and he's going to give his talk in the airport. So what are the goals of the UNSOUND workshop? So our goal is to discuss all aspects of unsoundness in type systems and verification systems, and to have a discussion about what these sources are and how they can be addressed. And we also want to discuss previously known or new sources of unsoundness and how they affect the day-to-day of researchers, but also actual programming language users. So in this welcome, I will just quickly introduce the subject matter, give some historical background, and a preview of today's talks. Okay, so first of all, what is unsoundness? It's good to be clear about what we mean here. What I think is a good way of describing it is that it's a mismatch between what the type system of a tool or what guarantees a tool is supposed to give you and what actually happens in a real system at runtime, for example, right? And so a sound tool will validate a subset of the correct behaviors. It may not be complete, so it may not be able to validate all of the correct behaviors. And an unsound tool will actually include some incorrect behaviors and while telling you it's correct, right? And so one of the most well-known historical examples of unsoundness is in languages like Java or C# or many others where arrays are covariant. And so this is a problem, right? It is a source of unsoundness, as I just described it, because it makes the type system claim things that are just not true. So basically, the covariance of array means that if you have a type string that's a subtype of object, for example, then it says an array of string is a subtype of an array of objects. And this is a problem because if you consider this example, if you create an array of strings and then you upcast it to an array of objects while still retaining the original reference, XS, it allows you to insert elements inside this array that are not actually strings, because the upcasted type says this is an array of objects, so you can insert objects into it, and 42 is an integer, which is an object. But then the original array still points to the same thing. The original variable still points to the same array. And so the same array is going to now receive values that are not actually strings. Okay? So it's a problem with interactions between mutability and subtyping. Another famous historical example is that of covariant method parameters. So at some point in the 90s, people argued that you could refine the types of class methods, so that, for example, if you had a base class that had a function foo taking an object and returning an object, you should be able to make a subclass where foo is refined to take a string and return a string, right? And it kind of makes sense with this natural idea of refinement. And many programming languages actually originally had that, including the FL programming language. But it's also unsound. For example, take this very simple example where we refine the type of a function, including the type of its parameter, so that it then accesses the length of its parameter, which is assumed to be a string now. But again, if you upcast an instance of this class, losing information about that refinement, then suddenly you can call the method with objects, including integers, and you have a problem again. Okay, so this one doesn't even use mutation, but it's a very similar kind of problem. So there are better solutions to this kind of problems, right? So instead of using covariant mutable arrays, you can distinguish between mutable and immutable arrays, separating their different interfaces, and then you can have the subtyping relationships you want. So that, for example, a mutable array is actually a subtype of a mutable array of string is actually a subtype of an immutable array of object, right? So a read-only array of object. That's fine. It's sound. And for covariant parameter type refinement, actually what you probably want is something like type classes, or alternatively f-bounded type parameters or multiple dispatch. Well, there are many ways that you could solve this problem without having unsoundness. A fun fact about TypeScript is that it has both sources of unsoundness. Okay, so it has both covariant arrays and covariant parameter. In fact, it has bivariant parameter refinement. And that's because really TypeScript is more of a linter, right? It's not really providing you any strong guarantees or any guarantees at all. And you can summarize the design philosophy of TypeScript type system as YOLO, right? You only live once. So there's an interesting talk by the creator of TypeScript where he describes how recursive types are checked for subtyping, and basically the TypeScript type checkers, TypeScript type checker expands the recursive types a given number of times, and then it gives up. But when it gives up, it doesn't throw an error. It just accepts that the subtyping probably holds, and that's of course unsound, right? And again, there's a better way of doing things if you do care about the guarantees. So, for example, you could restrict the recursive types to be regular, or alternatively parametric, which makes subtyping decidable, so you don't have to stop and just give up. All right. On the other side of the spectrum, soundness may be very important, right? So in verification, if your system is unsound, because of the principle of explosion, basically you can make it prove anything you like. So that defeats the purpose of verification, most probably. And in the last UNSOUND workshop, actually, we raised an issue with object-oriented programming and some verifiers that support object orientation, and that were found to be unsound, because actually object orientation does interact in possibly surprising ways with soundness, with verification, right? So we actually have a talk this afternoon about this problem and how we can solve it by using a better principled approach to deriving an object-oriented system from a functional programming one. So when does unsoundness arise? As you can tell, it arises when different features interact. So features in isolation may look fine, but when you put them together, suddenly problems occur, right? And it's often unsuspected. Often you see different things that seem completely fine on their own, but when you put them together, bad things happen. For example, side effects, right? Mutation and exceptions, they make many things unsound, actually, that would be sound otherwise. So typical example here is a polymorphic generalization in ML, right? If you generalize the types of values without a value restriction, then you get problems. But also you have problems in metaprogramming and path-dependent types and things like that. I highly recommend this website by Stephen Dolan with help from a few other people, which has a very good list of examples of unsoundness in type systems. It's very fun. You can see that many of the examples I talked about are, actually all the examples I talk about here are in this website, and they're well documented and well explained. And a favorite of mine in this list is when two obviously orthogonal features interact, which are generalized algebraic data types, which support a kind of reasoning that we refer to as GADT style reasoning on one hand, and multi-stage programming on the other hand. which are completely different things, right? So one is a type system technique that tries to discover more type information at runtime based on what you pattern match by refining the types of the scrutinies. And on the other side, you have multi-stage programming, which is just a technique of generating code while making sure that the output is well typed. And so here's probably the most concise way of expressing the problem is in Scala. It's not exactly using a GIDT, because in Scala GIDTs take a bit of a different shape, but it basically explains the source of the essence of the problem. So here we have an abstract class that has a type member, right? So this type is attached to all individual instances of the class, and each different instance may have a different type definition for A, okay? And we are giving it two bounds, one lower bound and one upper bound, and these two bounds are not consistent, right? So this lower bound says A should be greater than any, but it should also be a subtype of nothing. So n is like the top type, and nothing is like the bottom type. And this is obviously not true unless your type system has only one type, right? So basically, you cannot create objects. You cannot create instances of this class, right? It's like an uninstantiatable class. And in type systems, like Scala's type system, you cannot really statically prevent such bad bounds from being expressed. It was tried for a long time, and it's not really possible to statically prevent all bad bounds. And so as long as you have bad bounds, you have a problem with metaprogramming, which is exemplified here. So here we have a little tick before the curly braces, meaning it's a quote. So it's building a new program representation at runtime. And that program is a lambda abstraction taking parameters x of type t and returning a body which is evaluated as follows. So the dollar sign basically escapes the quotes and evaluates something at code generation time. And here we are just providing the value 42 and saying, oh, by the way, this has type x.a. Okay, and so what is x.a? Well, it's a type we don't know because we don't know anything about x. We just know it's a t, right? But we know it's greater than any, so surely 42 is less than a, right? We also know that it's less than nothing, so it's good enough as the type of the result here. And that's a problem because it means you're going to generate code that's actually ill-typed. And you could even crash the program generator itself without even running the generated code. Because the source of the problem is that it's fine to have bad bounds in Scala, provided that you can only use them when you have an evidence that the type is inhabited. So when you have a variable of that type in scope. But here, the variable is not actually there, right? It's only there in the future stage. So this code will never actually, this function that we're building will never actually be called. But because we escape the body, we escape the quote and we execute code directly, we are making use of a value that doesn't exist. And so it's not an actual proof of the property that any is less than nothing. Does this make sense, or do you want me to explain it a bit better? Yeah. And so what I found particularly interesting about this bug is that it arose in OCaml first. Someone found it in OCaml. And we could directly port it to Scala, which is a completely different language. So I opened an issue in the Scala repository, and it's still open to this day. What's really interesting is that OCaml and Scala basically share nothing in terms of foundations. They have very different foundations, right? So OCaml is basically a simply typed linear calculus plus some other bells and whistles, right? Like row polymorphism, recursive types, and GADTs. And in particular, it doesn't have implicit subtyping, and it has problems with types like top. So it doesn't even have a top type, which would cause problems. But Scala 3, on the other hand, is like fully subtyped. It has a top type. It's based on a completely different foundation where functions and type parameters are not even first class. They're like syntax sugar. And so it's funny that even though the foundations are completely different, you have essentially the same bug that arises in these two contexts, right? Okay. So let's look back at this historical example of a bad subtyping relationship, array of string less than array of object. Actually, we can make it sound by making sure that the array is linear, right? So this actually works. It is fine to say that this subtyping holds as long as array is linear. So why is that? How can you understand this? And this is one of the things I will talk about this afternoon in my contribution to the workshop. It's related to eta expansion and how to understand subtyping. Okay? And I would like to conclude with a quick note, because we are already out of time. I think that the notion of safety is relative, okay? Soundness itself is a bit relative. And for example, you can consider that, well, obviously we all know C++ is very unsafe, right? And it can lead to vulnerabilities and memory corruption. And so if you sandbox things by putting everything in WASM, for example, it's obviously safer, right? The program may corrupt its own memory, but it's not going to cause problems like vulnerabilities in the outer program. But it may still corrupt its own memory. On the other hand, if you build your programming language on the Java virtual machine, as long as you don't make use of unsafe APIs, which most Java programs don't really do it, or at least not directly, and certainly most Scala programs don't do it, then you have even more safety, because the program may no longer corrupt its own memory, right? So it's like a very safe little sandboxed runtime where unsoundness doesn't matter as much, right? Because if your type system is unsound, it's not going to lead to memory corruption and possible vulnerabilities. Rust, on the other hand, is often touted as a very safe language, right? Because it guarantees lots of things at compilation time, such as memory safety. Or does it? Well, not exactly, because it has many holes, right, in its type system. And a hole in the type system of Rust is much more serious, because it doesn't have this sandbox and this background guarantee about the programs and their memory. And so when this paper came out, Scala and Java's type systems are unsound, it generated a lot of talk, and it was kind of sold as like a very bad result, like, oh, we found out Java and Scala's type systems are unsound, they're worthless, right? And a lot of people have used this to criticize Scala, for example, to discount it, right? But actually, there were already many existing cases of unsoundness, like coherent arrays, and null itself is kind of unsound, right? Null is a value that says it has any type, but actually it doesn't really. If you use it, you have an exception. This is basically unsound, right? And so this paper isn't really that new, and it doesn't say as much as it appears to, right? And yet another source of unsoundness that we found recently will be presented in this workshop. It's about inner classes in Java. So you can attend it to know more. And I will just conclude on this note that most practical programming languages have plenty of sources of unsoundness, right? Some are well known and avoided by programmers, and some are not actually known, and they may cause problems. And so that's how I will conclude this introduction. And so let's talk about these problems. Okay? Thanks. All right. Any questions? So we don't have much time. No Discord questions, right?
No Discord questions.
All right. Okay. Yeah. So.
Back at 11.
Okay.